Good evening, one and all. I am Engineer Anil Baliga from Indian Concrete Institute, Mangalore Center, representing the entire galaxy of members of Mangalore Center. And today we have gathered here for the webinar series number 45 from QCrete Concrete Readymix India Private Limited. And today we have one of the most interesting topic for the day, and we have in fact we have been waiting for this topic since it was announced, and I would like to first of all welcome Professor Kohler, who is the expert in the subject, and sir, it's the first time we are having the international speaker, and we are all excited to to listen from you. And without wasting much of the time, I welcome you to this gathering. And at the same time, I would like to welcome all the attendees, members of Mangalore Center, ICI Mangalore Center, and the staff from QCrete Readymix India Private Limited. And yes, let us not waste the time. Sir Kaushika sir, over to you. Thank you so much.
Yeah. I can say it is a kind of an honor for us to have Professor Konstantin Kohler today with us, and it gives immense pleasure for someone like me from QCrete Readymix India Private Limited to introduce Professor Konstantin Kohler, who is working currently as head of the department Building Materials, Performance and Technology, National Building Research Institute, Department of Structural Engineering and Construction Management, Faculty of Civil Engineering and Environmental Engineering from the Technion Israel Institute of Technology. So it is a very prestigious institute in Israel. And he is also scientific director of Technion Recycling Initiative, co-leader Research Center of Sustainable World, Guangdong Technion. Dr. Konstantin Kohler was born in 1957 in Moscow, and he is an Israeli citizen from 1990. He has done PhD in structural engineering, Moscow State University in civil engineering, and he is working in Technion University from 1991. And he teaches numerous subjects: building materials, processes related to construction, materials and technologies, composite materials in construction, advanced chapters in cementitious systems, recycling in construction, and he talks, gives lectures on durability of building materials, and looks after laboratories also. And he is also heading non-destructive testing of concrete, and he has also teaches a lot on radiation safety in construction. He chairs 3 expert committees on non-destructive testing, radioactivity of building materials, lightweight aggregates, and 3 technical committees: concrete materials and products, steel for reinforcement of concrete, and ecological aspects of construction in the Israeli Institute of Standards. Coordinated the academic consortium with the aim to create National Research Center on Recycling of Materials by the call of the Israeli Ministry of Environmental Protection. He is active member of several European committees, and he has taken a lot of actions related to construction materials and ecology. TU 1301, Norm for Building Materials Network, Norm for Building TU 1404, towards the next generation of standards for service life of cement-based materials and structures, CA 15115, mining and European atmosphere, Minia, CA 15202, self-healing as preventive repair for concrete structures, Sarcos, CA 18112, mechanochemistry for sustainable industry. He has edited 2 international journals, Materials and Structures, Cement and Concrete Composites, edited special issues of Journal of Environmental Radioactivity and of Construction and Building Materials, Fellow of RILEM, International Union of Laboratories and Experts in Construction Materials, Systems and Structures, member of ACI, organized several RILEM conferences, including those on early age concrete and on concrete durability and surface life planning in 2006, 2009, 2020, co-organized the final symposium, Use of Byproducts in Construction, Dealing with Natural Radioactivity, 2017, Rome. The list is big. I think it will take another 10 minutes to read out his accomplishments. He has reviewed many technical papers, 60 international peer-reviewed referred journals and research foundations, has authored more than 100 peer-reviewed papers in international journals and more than 80 papers in proceedings of international conferences, authored, edited more than 30 books, which is a very big number, and book chapters, authored 6 patents and patent applications. The list is very big, as I said, and it will not be sufficient even if I go on reading his biodata for another, it will take another 10 minutes. So with this, we welcome all the participants and Dr. Kohler. As I said, he has taken his time out. It is a holiday for him on a Friday in Israel, but we are thankful to him and we welcome you once again, sir. Please, the floor is yours. Thank you.
Thank you very much, Mr. Kovshik. Do you hear me well?
Yeah, thank you. Yeah.
Thank you very much for your introduction. It's my pleasure to share with you by some results and by some thoughts about one of the interesting, in our opinion, novel technology of curing of concrete. But I would like to start my presentation with some basics. So first of all, I'm coming from the National Building Research Institute, which is a joint venture between the university, the Technion, and the Ministry of Construction and Housing. The university is located in nice city of Haifa, which is located in the biblical Mount of Carmel, surrounded by the sea from three sides. This is one of the slopes of the Mount Carmel. Can you see my mouse, for example, moving? I think you can see it. This is the Faculty of Civil and Environmental Engineering, and this is National Building Research Institute. This is computer science, and this is architecture building, and many other buildings which are not seen. This is a leading polytechnical university in Israel. We are a very small country with only 9 million people population. We have 7 state universities. I would like to give some credit to one of my former students. Now it's a faculty member, Professor Jensen, which is my colleague and friend from Denmark. And I'm referring some materials from the book of Kosmatka et al. And I will use some more technical materials for explanation. So the outline of my presentation is following. So I will start with some basics about curing, about hydration of cement, about chemical shrinkage, autogeneous shrinkage. Then I will go to external versus internal curing, IC, giving you some examples and discussing in the end how we can optimize internal curing. Starting from very beginning, from definition. So curing is a maintenance of moisture and temperature for a period of time after placing to ensure desired concrete properties to develop. This is a definition, but there are some keywords I would like to emphasize. First of all, we need to know what is the period of time to implement curing, what should be the temperature optimum for getting the desired properties, and moisture. So these are the three keywords underlined in this slide. And now I will speak about desired concrete properties. What are they? We are speaking about strength, durability, and beauty, aesthetics. You see, this is a kind of strength, durability, and finally, beauty, aesthetics. So concrete structures, especially if they are exposed, not plastered, not coated, they should look nice. In Israel, in our National Institute of Standards, we are trying in the last 20 years to adopt as much as possible Eurocode and the European standards. Eurocode, I'm just citing from Eurocode about curing. Concrete shall be cured and protected to minimize shrinkage, mainly plastic shrinkage in very beginning, to ensure adequate surface strength, adequate surface zone durability, again, strength, durability, protect from harmful weather conditions, from freezing, which is not very relevant, I believe, for most of the areas in India, and Israel is also considered as a hot country, but in principle, we build concrete structures in many countries with half a year or maybe even more winter. So, and then there is a need to protect from freezing, from harmful vibration, impact, or any other damage. And this is just illustration of the types of cracking we usually have in concrete structures. So we have different types of cracking, from plastic settlement happening in very early age of ours, plastic shrinkage, early thermal movement, which is very popular reason of cracking, coming later, starting from days, drying shrinkage, which is observed usually in the age of weeks, months, and years. And this is the main shrinkage component, which is considered by designers. Excess loading and corrosion. There is a need to plan and execute curing. It's not something easy to do. We need to understand there are different standards. We need to make some calculations. We need to design properly. So this is a real science in our area. Let's start speaking about the details. What is the necessary curing time? Usually we are speaking about hours, days, and weeks. The answer in our standards is simple. Typically, the standards discuss 1 to 10 days curing time. And what is very important to emphasize, we need to start curing as soon as possible. And another very important word is continuous curing. Trying not to have any breaks, any pauses in curing, continuously curing. From very early age, we know very well how Portland cement is hydrating. So we have 3 hours and 10 hours microphotograph. So we can see the hydration products are growing outwards from the cement grain. The porosity is changing, is reducing. And instead of the pores, we call them capillary pores. We have newly formed hydration products. Very often they are they are noted as CSH, calcium silicate hydrates. And this calcium silicate hydrate phase is the decisive phase of the strength. It's a strength bearing phase, but it doesn't form very early, so it needs some time. The first period is called dormant period, when nothing has happened. It's because of the need to regulate the setting times to provide a possibility to work with fresh concrete. I'm speaking about transportation, casting, vibrating, finishing, all kinds of technological operations with very fresh concrete. And strength starts growing in a few hours after so-called setting time. But I don't want to go into details now. We have different setting times, initial set and final set. But in principle, we are speaking about hours and then days. And different phases are formed in parallel to the main strength bearing phase, CSH, calcium hydroxide, which is responsible for alkalinity, which is a nice thing from the point of view of protecting the steel reinforcement from corrosion. We have other phases, monosulfate, ettringite, and many others. Heat of hydration can be effectively used to map the progress of hydration. We distinguish between these 5 phases: initial dissolution of solids, induction period, acceleration, deceleration, and steady state. This is illustrated in the next slide. In the beginning, stage 1, we have a little bit higher heat than in the following stages. It's because of dissolution or initial hydrolysis. Then stage 2, like I explained you, it's a dormant period related to initial set. Stages 3 and 4, indicating the C3S, it means halide hydration, the main mineral usually in Portland cement, and C3A also. And deceleration, when formation is decelerating of hydration products. And this phase is determining the rate of early strength gain. And then slowly, the hydration products are formed and the strength increases. Different minerals, halide, C3S, belite, C2S, tetracalcium aluminoferrite, which is cellite or ferrite, and the only mineral which doesn't have an abbreviated name, C3A, tricalcium aluminate. All of them, they have different kinetics of hydration. When we speak about hydration, we understand well that cement hydration, like hydration of many other mineral binders, also gypsum and lime-based systems, is exothermic with liberation of heat. Concrete is an insulator, and heat of hydration can be either detrimental, for example, when we have thermal gradients, especially important for mass concrete structures, resulting in cracking, but also helpful, especially in winter time, in cold regions, which provides activation energy when concrete is in cold weather, and resulting in early strength. Temperature of curing is extremely important parameter. We cannot cure under too low temperatures. Otherwise, you can see the crystals of ice. Portland cement doesn't react with ice. Even more, above approximately 400 degrees, we can neglect by the hydration rate. It's almost zero. And not too high. Because if you have too high temperatures, we can make some damage for the hydration products. I'm speaking about mature age strengths, not early age strengths. You can see this is a diagram. I took it from one of the teaching books. I think it was the Mendes and Diamond. And then you can see there is kind of optimum, and optimum temperature is between 10 and 20 degrees. I know that in India you have in many places higher than 20 degrees, but it's okay 30, but not very, very high, not very high. Then I just would like to remind you the popular concept of maturity. We have different formulas illustrating the maturity. The most popular, I think, in the literature, in the teaching books and standards is this formula when temperature is corrected by 10 degrees of centigrade. But this is a kind of empirical correction. And this is a curve which is very familiar for all concrete technologies, illustrating the dependence of strengths versus maturity. And doesn't matter what kind of temperature was implemented during curing, you see, but all the points are lying on the same curve, which is very nice to predict, for example, when we need to demolish structures, when we can release the stresses from the reinforcement, from the cables, for example, if we are speaking about pre-stressed concrete onto concrete. So there is a very, very important meaning of this maturity curve. And different companies, I don't want to make any advertisement for this company, but many companies produce this kind of instrument indicating immediately the maturity. And then most of my presentation is devoted to moisture. We know well that we need to keep concrete moist. Keep it moist. This is a rule. You see, the different phases I spoke about before, C3A, C3S mainly, and C2S, they need relative humidity is enough higher to hydrate. And in very dry climate, in very low relative humidity range, we can neglect by the formation of the hydrates because there is no chemically held water, nothing. Water is very important component, as we all know, in concrete structures, in concrete compositions. Of course, concrete is wet, at least at very early time. So we have extra water. In many cases, not all this water is needed for hydration, so we have too much water, and this water will be eventually evaporating. This is so-called free water. Free water, just to remind you, is a mixing water that has not reacted with the cement phases. It's not a part of the structure. It's not a part of these phases. But in addition to free water, we call this water often capillary water, which is located in these so-called capillary pores. We have physically absorbed water. I'm just following the model of Sereda. Physical adsorbed water and interlay water. So we have different kinds of water, free water and physically adsorbed water, including interlay water. Bound water or chemically bound water is chemically combined in the solid or physically bound to the solid surfaces. A reliable separation of the chemically combined from physically adsorbed water is not possible, unfortunately. But therefore, Powers in 49 distinguish between evaporable and non-evaporable water. All non-evaporable water is considered as bound water. And all evaporable water is not necessarily free water. So this is just reminding you the basics coming from classic work of Powers. And a few words about hydration. Hydration of these four main minerals of Portland cement is explained on this and the next slides. First of all, halite and belite. These are the minerals representing the most of the composition of normal Portland cement. The first row illustrates the reaction of halide or C3S, tricalcium silicate. And the halide reaction is explained here in the next row. Both produce CSH, which is the main strength bearing phase, and CH, calcium hydroxide, as reaction products. More heat is evolved during halide. You see the heat 500 joule per kilogram. C3S hydration is more rapid, contributing to early 8 strengths. But halide hydration occurs more slowly and contributes to the strengths after 1-2 weeks. In this slide, we can see the reactions of calcium aluminates. This is a little bit more complicated than you could see in the slide before. In principle, the teaching books list 3 reactions. First reaction is very fast. We can read in the teaching books flash set. Liberates much heat very fast. You need to retard this reaction. Otherwise, Portland cement products can set inside the mixer. And then we have gypsum. You can recognize gypsum formula. It's a calcium sulfate dihydrate. D means 2 molecules of water are a part of the gypsum crystal work. Of course, this reaction consumes a lot of water. And then we have ettringite. Sometimes ettringite is called, just to remind you, as a concrete microbe, or something which is very hazardous because it expands, but you can see the number of molecules of water in the formula. So it has a huge expansion. And then when gypsum is ending, the C3A, which is still a part of Portland cement, starts reacting with this ettringite. And these 2 products are, how to say, eating each another. And then we have a relatively quiet, not making any problems mineral, which is called monosulfate. Monosulfate because you see only 1 part of calcium sulfate is here, in contrast to 3 parts of calcium sulfate in the ettringite formula, with only 12 molecules of water chemically bound. So these 3 reactions are extremely important to illustrate the need to retard Portland cement with gypsum. Non-available water, if we calculate it using, for example, stoichiometric calculations, is different for different hydrates. But in principle, if we coming to the average, to the weighted average of the non-available or combined water content, we are speaking about water to cement ratio just for having this bound water between 0.23, 0.24 only. But this is a part of the water relative to cement, which is needed to form hydrates. But unfortunately, or maybe fortunately, I don't know, we will discuss it later, this very low water cement ratio is not enough to make complete hydration of Portland cement. We need to take care of the physics of the porosity, because if there is no room to accommodate this expansion of the newly hydrated products like CSH, the reaction will stop. And then for having the total minimum water cement ratio needed to complete reaction of Portland cement with water, we are coming to 0.4 approximately water cement ratio, which is much higher than this chemically bound water to cement ratio. Sorry. Now I would like to introduce the new term, which is chemical shrinkage. This is extremely important component of shrinkage, and I'm coming slowly to the internal curing of concrete. This chemical shrinkage illustrates internal volume reduction. This is a diagram illustrating the volumes of cement and mixing water before hydration, and this is after hydration starts. Part of the volume is reduction, which is illustrated by chemical shrinkage. And the magnitude of this chemical shrinkage is relatively high. By powers, in different works of powers, we can read different numbers, but he spoke about 6, 7, 8%. So this is not per mil, not microstrains, which is used by structural engineers to design the structures. It's several orders of magnitude higher. So volume of reaction products is known to be smaller than the sum of the volumes of reactants. And this is our chemical shrinkage. The first researcher and engineer, by the way, he was in parallel, brilliant researcher and brilliant engineer, was Le Chatelier, Louis Le Chatelier, French, Italian chemist. He came from the mixed family. Maybe the mixture of genes is responsible for the brilliant contribution of Louis Le Chatelier into different areas of cement and concrete science and engineering. He discovered this chemical shrinkage more than 120 years ago. In 1900, he published a famous work explaining what is chemical shrinkage. What is the practical importance of chemical shrinkage? In concrete with very low water cement ratio, I'm speaking about high strength, high performance concrete, chemical shrinkage results in self-desiccation and autogeneous shrinkage, which can lead to cracking and even failure. Chemical shrinkage basics. For example, let's consider the hydration of tricalcium silicate, halide. This is just stoichiometric equation explaining what we have as chemical shrinkage. So this is very known for the concrete technologies. I would like to go quickly further, but everything is nicely described by mathematical formulas, because chemistry is a kind of mathematics. Then I would like to explain you briefly how Le Chatelier measured this chemical shrinkage in his experiments and how we can measure it now. This is very simple test he did. He took a flask, cast a very thin layer of cement paste in the bottom, filled with water, and followed after the rise, not rise, but the drop of the meniscus in this very, very thin tube. And he discovered then from following after the meniscus drop, he understood that some water is disappearing, so-called disappearing. It doesn't evaporate because these conditions were not characteristic for evaporation. So water didn't disappear, but what happened? Where water went to? And he understood the water filled the internal pores forming in the system. And so chemical shrinkage is a reduction of volume, which is internal volume reduction, internal. It is very difficult to see it from outside. So we have another method of measuring chemical shrinkage by using the this test by weighing this flask with the sample inside water. So this is very simple test. We can do it with a very, very accurate balance with accuracy of at least 1,000th gram. It would be nicer to have more accuracy, to have high accuracy. This shrinkage, chemical shrinkage, is accompanied by autogenous shrinkage and self-desiccation. Self-desiccation is a direct result of autogenous shrinkage. This diagram was taken from one of the works of Professor Jensen from Denmark. You can see addition of silica fume increases the self-desiccation, and relative humidity in the system is dropping. What is the difference between chemical autogenous shrinkage? I would like to say a few words about the difference. So again, chemical is inside the system. You can see this newly formed pores by white, you see? And autogenous shrinkage is a shrinkage which can be registered from outside. Of course, the magnitudes are completely different. You will see later on the typical results of measuring autogenous shrinkage. And then how to measure this volume reduction? This volume reduction is measured by using a so-called condom test. Yes, this is a very popular test in the labs. We have to fill this condom with cement paste, for example. Or by the way, there are big condoms. I'm serious, which are used for horses, for example. Yes, I saw these condoms in the labs for measuring volume changes in the concrete or mortar specimens. So this specimen located in the membrane, which is a condom, is immersed in water. By the way, instead of water, we recommend to use more viscous liquid like oil or paraffin oil, which is less penetrating. And then a few words about different components of shrinkage. So till now, I spoke about autogenous shrinkage, which is a result of chemical shrinkage, but all these shrinkage components are measured from outside. This is external volume reduction, external volume or linear reduction. Autogenous shrinkage is a very important component, mainly in high strength concrete, HSC. Of course, we know well what is a plastic shrinkage, what is a drying shrinkage, what is carbonation shrinkage, observed in very external layer of concrete, and thermal shrinkage, because most of the construction materials have different coefficients of thermal expansion. So, and we cannot avoid thermal fluctuations in the ambient air. And concrete, by the way, during the hydration can change the temperature. So we have different temperatures, ambient air and the concrete temperature. So we need to take care about these thermal components as well. This is a scheme. We published this scheme in the first time in the report of the technical committee on internal curing of concrete. I chaired this committee for 5 years in Raleigh, and this diagram is easily found in this report. I recommend to anybody which is interested to go into details to see this report. It's available, by the way, from the Raleigh website. So curing of concrete technology is divided by two different groups: external curing methods and internal curing. Please look, I'm speaking now about the curing aimed to maintain moisture content. I'm not speaking about temperature here, only moisture. External, which is subdivided by water curing methods and sealed curing. The same subdivision can be seen in the right part of the slide. internal water curing, and internal sealing. I believe most of our students and engineers and researchers know well what are the common methods of water curing. They are water ponding, spraying, fogging, saturated coverings. Sealed curing is divided by different methods: waterproof paper, plastic sheeting, curing membranes, and so on. Internal curing is also can be divided by using lightweight aggregates, LWA, super absorbent polymers. I will speak about these technologies later on. But please look, even normal weight aggregates like sand can be considered as an internal water curing agent when this aggregate is introduced in the concrete mix in water saturated condition. Wood-derived products, including different byproducts of wood industry, recycled aggregate, which is a porous, by the way. Internal sealing methods are still on the research laboratory shelves. We have this method described in several papers, but it's still far away from being implemented in the industry. But these methods, especially lightweight aggregates and superabsorbent polymers, especially the first one, are already in the practice. Water curing, just to remind you about ponding, spraying, fogging, saturated coverings. All these technologies are conventional. They are very famous. They are very popular in the concrete industry. Fogging, I'm going quickly because I have a large number of slides to go over. Seal curing, this is just an illustration of different systems. Waterproof paper, plastic sheeting, for example, polyethylene sheets, and membrane forming curing compounds, which can be sprayed from outside. These prevent evaporation of concrete, all these methods. Of course, the workers should be protected by special masks because some curing compounds are toxic, and we need to take care. Now I'm coming to high strength or high performance concrete. First thing to mention would be minimum bleeding in high performance or high strength concrete. Minimum bleeding. And this bleeding is very important to compensate evaporation of water when we speak about plastic shrinkage and plastic cracking. This shrinkage is extremely important for very hot climate, and not only for very hot climate. It can happen easily in very cold climate when the wind speed is high. For example, in Norwegian fjords, we have extremely high wind speed. So the evaporation rate is a direct function of the wind speed, of the temperature, by the way, not only from the air, ambient air, but also depending on the internal temperature of concrete, and relative humidity of the air. All these four components are extremely important, and this evaporation can be nicely compensated by bleeding. So in this sense, bleeding can be sometimes very positive, in spite of the fact that most of builders, most of our researchers and engineers consider bleeding as something hazardous. But for example, for concrete pavements, when we have a high surface of evaporation, it can be nicely utilized. So plastic shrinkage happens in very, very early time. Then we have, after initial set, autogeneous shrinkage, when capillaries are emptying, and this should be avoided, of course. And when we have steady structural formation, in a few days, we have starting drying shrinkage. Of course, we need to avoid it, because autogeneous shrinkage develops until hydration stops, and we have impervious film. So in principle, we need to take care of both autogeneous and drying shrinkage when the age of concrete exceeds hours and days. So again, moisture, external methods for maintenance, But why not external curing for high strength concrete? First of all, external or conventional methods of curing requires extra labor. We need to take care about quality assurance, quality control and insurance. Insurance, by the way, is more important than control. We have, in many cases, inaccessible surfaces. And especially when we discussing high strength or high performance concrete made of very low water cement ratio, this concrete is low permeable. It means the concrete implemented, applied from above, from outside, cannot penetrate too much, too deep, more than 2-3 millimeters. You can neglect by penetration depth, so it doesn't help to cure. And then all the idea of internal curing is introducing, how to explain you, a kind of Trojan horses, something which is acting from inside. This material or this additive or mixture can be called internal curing agent. It should be porous because it should accommodate, it should contain some water. But please look, this water is not a part of the mixing water. It should be deliberated slowly during the hydration process, but not immediately, not immediately. And pumice, we worked a lot with crushed pumice. I explain you some results later on. And expanded shale aggregate, both of them are illustrating the porous structure of the aggregate, can be nicely used as internal curing agent. Lura in 2003 tried to measure how deep, how far this water accumulated, located inside the particles of the porous aggregate, can penetrate outwards. So he used ink solution, and then he measured, for example, 1 millimeter is quite something. But for me, it's not very accurate experiment because we don't know exactly what was the kinetics. So we don't have any idea when this water deliberated from the particles. But for sure, it can deliberate and penetrate too far. We are speaking about millimeters. This is an electron micrograph of the typical structure of pumice. We worked a lot of pumice. In the beginning of 2000s, I tried to introduce pumice as a good combination of mechanically strong aggregate, which is not disintegrating during mixing. Otherwise, if you use very, very weak but very porous, we try to use, for example, perlite or some other very light porous aggregate with a lot of porosity, but very weak mechanically. And this aggregate can disintegrate during mixing, and then as a result, we have a dramatic increase of slump. So we can see the workability, the plasticity, flowability is changing dramatically. It is direct result of premature deliberation of water. So this is not good for us. We need to lock this water for a few hours, not to be considered as a part of mixing water. What is interesting, this pumice particle is formed from magma erupted from volcanic origin material, from magma, and then the hot gases penetrating through this volcanic origin material leave behind this open pores looking as tubes, very long tubes. So most of the porosity, and this is very important to understand, this is very needed for having efficient internal curing. Most of the porosity is open one. We prefer open pores over closed pores. And then please look what we have in the experiments with concrete after adding this pumice. Let's say we have reference concrete made of very low water cement ratio, 0.21. This is a dashed curve here. Extremely high autogeneous deformation, microstrain. You can see easily reaching almost 500 microstrains. This is a reference. If we have higher water cement ratio concrete, for example, 0.33, we still have some autogeneous deformation, and this is not good. But how to compensate it? In both cases, we introduced lightweight aggregate. For example, here we succeeded to completely combat autogeneous shrinkage, and here also. So this is kind of plateau with maybe very small expansion in very beginning. There are still some dispute among the scholars what is the reason of this very small extension, but this is not a problem. The problem is the shrinkage, because under shrinkage in restrained conditions the tensile stresses are generated, and concrete is not good under tension, as we know. This is another class of internal curing agents, which is called SAP, or superabsorbent polymer. You can see how the particles of this superabsorbent polymer look like. This is one of the examples. When it absorbs water, the dimensions increase dramatically. Usually, from chemical point of view, this superabsorbent polymer is hydrogel. And this hydrogel is mainly containing water. So the mass of the density of the particles of polymers, superabsorbent polymers, is like water. So most of the volume is occupied by water. Another kind of superabsorbent polymer, you can see another shape of the particles. It's not spherical one, but it's crushed angular particles. This is an example of superabsorbent polymer made of the main monomer as acrylic acid. This is produced by bulk polymerization technique and crushed. So you can see how the particles look like before hydration, before absorbing water. And this is what we have after adding water. So the volume expands. And this is, again, returning to the monomer produced by inverse suspension polymerization. Spherical particles. This is before absorbing water. Please look at the particle size. So this is 400 microns. So we have approximately 50, maybe 80 microns. So this is still not nanoscience, but this is a micro world. This is a microparticles. And then we did this picture under environmental scanning electron microscope, which doesn't require any vacuum. And then we can see how the absorption of water results in the expansion. So particles are expanding. This expansion is very fast. And it can happen in very few seconds after mixing with water. Very important issue is to calculate accurately chemical shrinkage to be compensated. If we compensate successfully chemical shrinkage, no autogeneous shrinkage is expected. How to do it? This is the total chemical shrinkage at the time of T. CS mean chemical shrinkage. CS here, it's a specific chemical shrinkage of the given cement. So this is a property of the certain cement. C, capital, is the initial weight of cement. And alpha is degree of hydration. Yes, we admit that alpha is not 100% because we are speaking about the first, let's say, 1 week of the concrete age. 1 week. In 1 week, we don't have 100%. We are still below 100% in our experiments. In 1 week we have approximately 60, maybe 70% of hydration, but not more, not more. And this should be considered in calculating the chemical shrinkage. When we know this chemical shrinkage, we can automatically calculate how much internal curing agent. It can be lightweight aggregate, it can be superabsorbent polymer, it can be other, for example, wood-derived product needed to add for eliminating self-desiccation and autogeneous shrinkage. How we calculate this content of the IC agent, internal curing agent? By a very simple formula. We need to know how much water is needed. This is not a part of the mixing water. It's extra water. We use IC as an index, internal curing water, per cubic meter of concrete, of course. All calculations are, of course, made for 1 cubic meter of concrete. C in this formula is cement content. CS, as in the previous slide, designates chemical shrinkage. Alpha maximum degree of hydration expected. And S, and this is very important to know, this is degree of saturation, because sometimes we have not fully saturated particles of internal curing agent, not fully saturated. Just giving you one example. We worked a lot and we published many papers using pumice as internal curing agent. We don't use too much pumice. It would be better to consider this pumice as additive, but not as aggregate. For example, we are using a few percent only. So this is not really aggregate. This is a kind of additive. And then to have fully saturated condition in pumice particle, we need to make a very special thing. For example, we need to make a vacuum saturation under vacuum, or at least we need to try to do our best to boil water. When we boil water, we can fully saturate particles within 3 days or 2-3 days. If we use vacuuming, vacuum saturation, we can do it very quickly. Let's say fully saturated condition is obtained within half an hour. When we try to saturate by immersing this lightweight aggregate in normal room temperature water, it can take months, 2-3 months to have fully saturated solution. Of course, it's not reasonable time, because every contractor counts time as money. But we know how to do this vacuuming, and this is not a big deal. So we can produce this apparatus very easily. So if anybody needs our recommendation how to produce it and how to increase the rate of saturation, it's not a problem. We can help you in sending recommendations, or you can see our reports. And ETA, which is also very important issue, it's called internal curing efficiency factor. How to understand what is the efficiency factor? It's I will explain you later on. But in principle, if I come back to the diagram of autogeneous shrinkage, you can see this is a ratio between the deformations. I'm speaking about the plateau. If we completely eliminate autogeneous shrinkage, the efficiency is considered 100%. If we eliminate 50% of the autogeneous shrinkage, so efficiency factor is equal to 50%. So this is very simple to understand, but we know how to introduce this efficiency factor in the formula. And then we have everything to calculate precisely how much this or that internal Curie agent should be added. Relative humidity, again, this is zero content of sap. Everything is calculated relatively to the cement content. When we add a little bit, just 0.3% of superabsorbent polymer, we almost succeed to compensate autogeneous shrinkage. If we put a little bit more, 0.6%, we have completely compensated situation. But of course, polymers cost money. So in comparison with lightweight aggregates, this technology is more costly. But it depends on the situation on the market, and more superabsorbent polymers are generated now and developed now in the world, and the price for 1 kilogram of superabsorbent polymer is reduced dramatically during the last 5 years. Autogeneous relative humidity can be measured by this instrument. And then this is a result of the same author, Professor Jensen. Again, 0% of superabsorbent polymer. This is deformation. And this is 0.3%. This is 0.6%. And this is an instrument to measure autogeneous shrinkage. It's called dilatometer, which was developed by Jensen and Hansen many years ago in '88. The principle is to measure, to be able measuring the deformation from very beginning, from the very fresh condition. So there is no need to demold the specimen. And this is the formula illustrating the internal Curie efficiency. So again, this is a ratio between the difference in autogeneous deformation relatively to the deformation in the reference system. Okay, so I'm coming back, and but most of our structures are not restrained completely. We have either complete restraint or fully restrained, and there is no freely loaded structure. And for characterizing the restraint shrinkage of the specimens, the authors developed different kinds of techniques: ring-based tests, plate, special tests for repairs, restraint by substrate, and uniaxial, for example, longitudinal or uniaxial. This is very common and very popular test for restraint shrinkage. It's called restraint ring test. You can see here, this was done by Grace Ambrosia, but in principle, this ring test is known for years, maybe for 70 years, because the first publications are available from 1950s in Portugal and some other countries. So this is very important and very simple techniques. So we are casting our concrete around the rigid core. You can see here, which is usually made of steel, which is a stiff, very stiff material. We can say this is stiffer by infinite number of times more than fresh concrete. We can neglect by modulus of elasticity of the fresh concrete. And then concrete starts to hardening, and deformation of shrinkage results in generation of stresses. We have radial, we have tangential stresses. This is very well known. It's explained in our papers and in the papers of these authors and many others. So this is very easy to calculate. We can do both autogeneous shrinkage in restraint conditions test and drying shrinkage. When we demold the specimen from all the sides, from above and from the sides, and it's shrinking towards the core. And then this is just a picture illustrating the appearance of the concrete ring. You see, which is located between the two rings, the internal rings, which is responsible for the generation of the tensile stresses in concrete, and the external ring, which can be demolded completely if we would like to simulate drying shrinkage. If we don't demold, if we work with sealed concrete specimens, so this is a simulation of autogeneous shrinkage. Autogeneous deformation should be measured under sealed condition and under isothermal condition. This is by definition. Please look into the report of our technical committee. This is the stress built up, illustrating the rise of the stresses in this ring when we have reference concrete containing zero, doesn't contain any superabsorbent polymer, and this sudden drop of the stress says that we have a crack. We have deliberation of the stresses, and we can see it nicely after this drop. So the system is completely automatic, so we can measure automatically. How we measure these stresses? By using strain gauges. You can see these strain gauges are installed on the internal surface of the steel ring. And then we are measuring the strains in the steel, but modulus of elasticity of steel is well known. And then we can calculate easily the stresses generated in the steel ring. And by some modeling, we can expect, we can calculate, we can assume the stresses generated in concrete itself, in this ring, concrete itself. So, and this is called stress built up in concrete. But again, this ring test is a standardized test. It's a part of ASTM standard. And when we try to introduce some internal curing agent, we have slower build up of the stresses. This is 0.3% of superabsorbent polymer introduced. Moreover, the lifetime of concrete is extended dramatically. We don't have within 2 or 3 weeks of the monitoring any cracks. And if we introduce a little bit more, 0.6% of superabsorbent polymer, we have almost complete combating, complete compensation of the stresses. Very nice result. No risk of cracking, nothing. And this is a very important issue, mainly for high strength concrete, for high performance concrete, which is made again with a very low water cement ratio. This concrete, as you may remember, was developed by the Japanese in the 1980s, immediately after they developed the first super plasticizers, and then it was possible to go very, very low to water cement ratio. But in the beginning, let's say the first 10 years, all the scholars and researchers and engineers were so much excited of having this high strength concrete that only in 10, 15, 20 years later, they understood that they have a problem of autogeneous shrinkage. This is extremely important to understand. The people who are not familiar with concrete technology, they are often surprised to learn that high strength concrete made of very low water cement ratio can shrink even cast underwater. Because again, water by conventional curing, water from outside cannot penetrate easily because of the dense packing, dense structure, microstructure of this concrete. Because water cement ratio is a primary factor governing, controlling the distance between the two adjacent cement grains. And the porosity is very low, the distance, the spacing is very low, the water from outside has a difficulty to penetrate too deep. And then, as a result, cement is a very interesting binder. Portland cement likes water. Portland cement is looking for water. If the water is ended because the self-desiccation starts, then hydration stops. And then we have two parallel events: self-desiccation, the dropping of the relative humidity in the pores, and autogeneous shrinkage. This is extremely important to understand. This kind of concrete made of very low water cement ratio is extremely sensitive to curing. And only internal curing can be a good solution for curing. External curing, conventional curing methods do not work perfectly. So, how to optimize the internal curing technologies? First of all, we need to get maximum efficiency of internal curing to get reduction, effective reduction of autogeneous shrinkage. I remind you the concept of eta factor, efficiency of internal curing. Of course, we need to remember that we need to provide cheaper solutions. We need to follow after the minimum cost. And again, if we speak about superabsorbent polymers, yes, 0.6% relative to cement content of superabsorbent polymer is nice, but it's double amount and polymer costs money. Perhaps in many cases it's enough to be satisfied with 0.3%. So this is a issue of optimization. So we need to make a cost-benefit analysis. And of course, we need to remember about the strengths, because if you introduce any agent, internal curing agent, which is a porous, it doesn't matter, superabsorbent polymer or lightweight aggregate, we expect a strength reduction, because the porous materials, it depends on the content, of course, on the concentration of the porous materials inside concrete. And this strength loss should be minimized. By the way, coming back to superabsorbent polymer, eventually these particles, when deliberate water, become porous, just pores, empty places. I have many macro graphs illustrating the pores formed after they deliberated, the particles deliberate water. That's all. And so we need to understand, we need to take into account this external, additional extra porosity. But fortunately, we have a trade-off. We have improved hydration rate. We have more, we have higher degree of hydration. We are recruiting more cement for cement hydration. And then it easily compensates, if we calculate precisely the amount of the material, take into account the water absorption and other properties, it can be easily compensated or this strength loss. So minimum strength loss is a very important topic in many papers, not in many, but in some papers, unfortunately, the scholars, the researchers put too much agent, and then it resulted in dramatic strength loss. We don't want to compromise all the technology of internal curing. So additional porosity is in trade-off with improved hydration. And we need to understand who wins. Practical recommendations. I am coming to the conclusions to avoid strength reduction. First of all, as we recommended at some of our papers, let's combine this internal curing agent with some pozzolanic materials. Do not add too much water. Use superabsorbent polymer as water retaining agent and keep your powder dry. This is extremely important for internal curing agent as superabsorbent polymer. And do not add too much this agent. Not only from the cost considerations, but also from the requirement of minimizing the strength lost. And conclusions. Let's do better curing, let's do better hydration, and let's have better durability of structures. Questions, comments, and feedback, please apply to the organizers. Thank you very much. This is all for today. So, Mr. Kovchik?
Yes, sir. Thank you very much, sir. Anjali will ask some questions which are asked by some of the audience. Anjali, madam.
Yes, sir. So the first question goes like this. Does the microstructure differs interior portion of the concrete and exterior portion of concrete, as interior concrete undergoes heat of hydration and prolonged moisture curing, whereas exterior concrete suffers lack of prolonged moist curing? And that was asked by Dr. B. Kamesha Rao.
I'd like to understand the question. You are speaking about two kinds of concrete, exterior application and internal. You mean bulk, right?
Yes, sir.
Something like, look, I didn't discuss these two different kinds of concrete in my presentation. I think there is not enough knowledge about this type of concrete structures. I spoke about the bulk concrete, not about the exterior. Exterior concrete, it's a little bit more complicated issue because the gradient of moisture is significant there. If you are, well, let's say 5, 10, 20 centimeters deep into the structure, you can neglect by the gradient of moisture. But I completely agree for exterior concrete, for the external layers of concrete, the gradient of moisture can be significantly different in comparison what is inside. But also we have to understand that we have other components of shrinkage. For example, carbonation shrinkage, which is not an issue for the bulk of concrete. It happens only in the external layers. So this is very, very complicated issue. Not only the moisture is different, but different shrinkage components. So I think this the answer, it depends on the progress in research. I don't want to promise anything, but this is certainly one of the fronts of the future research.
Thank you so much, sir. So the next question is, does internal curing compound has any negative effect on strength? And that was asked by Sarvesh Naik.
Yes, I addressed this issue. It was very good question. Thank you very much. In some papers, the authors report significant strength loss. But if you go, for example, to our paper, when we criticize dramatically these authors, this paper was published several years ago. I think it was published maybe 8 years ago, something like this, by 4 authors, myself, my young colleague Semyon Zhutovsky, and 2 authors from Denmark, Professor Jensen and his colleague, Marianne Hashold. We discussed the problems with organization of the experiments. These authors, unfortunately, made a dramatic error in calculation of the total amount of internal curing agent. They put simply too much. And then, as a result, they introduced a lot of water, which was much more than needed by precise calculation using my formula. Much more water, because if they measure water absorption in different conditions, it's very important for superabsorbent polymer, because absorption of water depends on the type of the water. We are distinguishing between distilled water and pore water, which contain ions. You see, and the absorption of water inside the cement paste or inside concrete is much less than water absorption, for example, in the typical laboratory test with distilled water. This is different conditions, you see, and then this can indeed result in dramatic loss of strength. We don't need it. This is very important issue to prevent it. But we can do it, and we can do it. Fortunately, the strength in 28 days and 90 days and 1 year in internally cured concrete is very often higher than the strength of the reference concrete. But again, using internal curing is not for strength. We can easily make very strong concrete in our lab, in the site, reaching 200, 250 megapascals even. It's not a problem. We know how to decrease dramatically using very efficient superplasticizer of the last generations. This is not in our task. Our task is durability improvement to prevent cracking because of autogeneous shrinkage. This is Achilles heel of the high strength concrete.
Thank you, sir. Sir, the next question is, how much is too much IC agent? What is the optimal use of IC agents, and what should be the range for IC agent dosage?
For superabsorbent polymers, the numbers are in the range of parts of the percent. For lightweight aggregates, it depends on the porosity, of course. If we have nicely developed open porosity, like in pumice, you can be satisfied with 6-7%. So in this sense, this is not a part of the aggregate, like I told before. So this is not a big amount of aggregate. So from the point of the view of the strengths, it doesn't change too much the strengths. So the magnitudes are different. Again, several percents in lightweight aggregates and several parts of the percent in superabsorbent polymer. But again, you need to check precisely the absorption and the efficiency. Go, for example, to our report. It's available for the public. You can download from the Rallium website. You're very welcome.
Thank you so much, sir. The next question is, how can we increase durability and curing period without increasing the water cement ratio? And that was asked by Atul Krishna CR.
Without decreasing water cement ratio, without increasing? I did hear you.
Without increasing the water cement ratio.
Without increasing, but we, yeah, yes, of course. Please look, I distinguish again between water cement ratio when we divide the amount of mixing water by the amount of cement. And I'm speaking in this presentation about extra water. And this is not a part of water cement ratio. This is a special WIC divided by C ratio. This is internal curing water to cement ratio. And this ratio is usually about 0.03, 0.04. Using my formula, you can easily calculate it. It's not, it depends on the water. So you have to precisely calculate the water for internal curing, and this is above the mixing water. Let's say you have 0.3 water cement ratio, I mean mixing water to cement ratio. And if you add, let's say 0.03, this will be the total water cement content. But again, we need to calculate it precisely because this internal curing water is not a part of the mixing water.
Thank you so much, sir. The next question is, why internal curing compounds are still not very popular? Any side effects or what?
Internal curing compounds. I didn't understand precisely the question. The question is about all kinds of internal curing compounds. They are different. We are speaking about lightweight aggregates, about superabsorbent polymers, about wood-derived particles, about recycled aggregates. So what kind of, I didn't understand. Can you please repeat the question?
Why, yes, sir. Why internal curing compounds are still not very popular? Any side effects
Are
or
still not popular. I see. But some of them are already popular, like lightweight aggregates. Lightweight aggregates, especially those with a very open structure, like pumice, like leca. If you know what is leca, this is lightweight expanded clay aggregate. It's artificially produced. I'm not aware about the production of artificial lightweight aggregates in India, but in Italy and many other countries, they produced quite well in big amounts. What about superabsorbent polymers? Yes, they're still costly, but it's already introduced in the practice. By the way, these superabsorbent polymers were a very interesting part of the business of one of the big companies producing cement in Thailand. It's a Siam concern. And they produced, I think they still produce the cement containing a minor part of superabsorbent polymer, in spite of the fact that superabsorbent polymer is still costly. Because in many areas of Thailand, I believe also in India, you have, also in Israel, you have, and we have problems with curing. Because of hot climate, because of very fast evaporation of water, and then the control of quality assurance is not very high. And then to compensate this problem of curing on site, it would be nicer to have special cement. So in spite of the cost of superabsorbent polymer, it starts penetrating into the market. But again, lightweight aggregates are much more popular, much cheaper than other. And again, wood-derived products, it's just byproduct. It doesn't cost too much. It's just nothing. And the recycled aggregates, also the cost of recycled aggregate is very low. By the way, if you use your normal weight aggregates in water saturated condition, it can be also a step forward. It can improve the durability, and it doesn't cost too much just to saturate this, for example, sand particles.
Thank you so much, sir. Next, we have a question asked by Virupakshaya SK, and the question is, what are the challenges in designing IC concrete?
The challenges is, again, minimizing the strength losses. And this is the reason that we need to precisely calculate the quantity of the internal curing water, and consequently the quantity of the internal curing agent, let's say lightweight particles or superabsorbent particles or whatsoever. This is a very important issue, especially for superabsorbent polymers. This is very important to understand that absorption of water, which is a property of the additive of internal curing agent, depends on what are the situation, what is the type of the water. For lightweight aggregate, it's easier, but for superabsorbent polymer, it's much more complicated, but we need to be very, very attentive to calculating. And then another important issue for the future development, research and development would be to find a combination of internal curing and traditional methods of curing and known admixtures, for example, shrinkage reducers. In some of our papers, we described the combination of internal curing, for example, pumice or superabsorbent polymer, with shrinkage reducing admixture. It works much, much, much better than each of these techniques separately. And we are starting to understand why. What kind of synergy we can observe in this interesting phenomena. Why the combination works much, much better than each of these methods separately. This is interesting issue. And also a combination of three types of the methods: internal curing, one, shrinkage reducer, it's known admixture, and mineral admixture, so mineral additives like silica fume or fly ash or slag. How this triple mixture can behave. So this will be very interesting for the further research.
Thank you, sir. Next, we have a question asked by Alex Daniel. And the question is, are there long-term studies done on internal curing compound incorporated concretes?
Long-term studies are not yet available because these methods are relatively young. They have been introduced recently, and then we have not enough statistical data and durability data, but we have several papers, very good papers published in different peer-referred journals, reporting the results of the, let's say, of accelerated tests of durability based on accelerated chloride penetration. Okay, it's a part of the durability study, and it works well. So we can simulate the long-term testing by accelerated testing using high temperature, cyclic loading, for example, the wetting drying cycles, combining with chloride penetration. So this is very similar to what is done in other durability related tests. So these data are available.
Okay, thank you, sir. Next, we have a question asked by Durga Prasad, and the question is, calculation of internal curing compound seems too much complicated. How can site engineers implement these easily?
First of all, let me comment on this. In my opinion, this is not very complicated. This is just introducing in the system some special agent, like a normal admixtures. Admixtures industry works well. We have many, not only shrinkage reducers and superplasticizers, we have accelerators, we have retarders, we have curing compounds, we have many interesting admixtures which penetrated nicely into the construction market. Internal curing agent is penetrating quickly now. By the way, we have already a standard regulating, it's American standard, ASTM standard, regulating the testing methods for internal curing. And when standard is published, it's already a big step forward because it makes easier in implementation. So what is really can be complicated, it's using the formulas and using the preliminary testing. You need to know precisely the properties, for example, water absorption. And this is, but again, it's not a big deal to make this test. Everything is known. So in my opinion, this is not very complicated. And for example, if we are going to implement more and more high strength, high performance concrete, this is the front. This is the issue. This is the issue. For normal strength concrete, maybe there is not no need, urgent need to implement these techniques. These techniques working well in high strength, high performance concrete.
Thank you so much, sir. Now we have the question, are SAP easily available for making internal curing compounds? And that was asked by Ramanathan.
Again, can you please repeat the question, because it sounds very general.
Sure, sir. Are SAP easily available for making internal curing compounds?
It's SAP, SAP, okay. No, there are only a few places, a few plants producing these superabsorbent polymers suitable for concrete applications. Most of SAP, SAP, superabsorbent polymers are available for other products, and diapers, for example. This is the main market. For construction, we need special superabsorbent polymers, yes, but unfortunately, till now, not much is available. Not much is available. But if you would like to learn more, I would like to recommend you to apply to my colleague and friend, Professor Jensen, which is I can say, a father of superabsorbent polymers implementation in concrete construction. And he did a lot of work, a lot of research on this kind, and compared many different kinds of superabsorbent polymers, and understood very well what is suitable, what is not. So if you want, just let him know, and I believe he will be pleased to answer you and recommend you a special superabsorbent polymer which is suitable for our applications.
Thank you so much, sir.
Sir, thank you very much, sir. I think most of the questions are answered. Our MD, Shalifah Nandis, sir, will do the vote of thanks.
Yeah, good evening, sir. Good evening, friends. Good evening, sir. We have come to the end of our very interesting lecture today on understanding internal curing of concrete by Professor Konstantin Kohler. He's the head of the department, Building Materials Performance, National Building Research Institute. Then he's working with the Israel Institute of Technology, actually. So with the number of questions asked, actually, it has exceeded the time, and the number of, it seems to be a very interesting topic, actually. This was our first international webinar and 45th QCrete webinar series, actually, conducted by QCrete Readymix India Private Limited in association with Indian Concrete Institute, Mangalore Center, actually. Thank you, Dr. Konstantin Kohler, for delivering informative talk and most relevant topic, actually. In India, the contractors, very interesting, is not paid for curing, actually. There is no measurement that by so much liters, if you add water, you'll be paid in that one. So most of the time, after the concrete is over, they forget the curing part, actually. And in this contest, we end up with a weak concrete structure. And most of the time, RMC players have a lot of hectic time convincing the contractors to do the curing, because we end up with a lot of plastic shrinkage cracks, actually, and end up fighting with the contractors when the crack appears, actually. So in this contest, actually, your topic was very relevant. Actually, might be it is little early stage, but in future, I think most of the RMC players can sleep peacefully. Might be adding a few of the compounds along with the when we are manufacturing concrete, and forget curing afterwards, actually. So in this contest, the topic was very relevant, and we could see a lot of questions being to be was shooted at you actually, and you had answered it properly. All the questions actually. Thank you very much, sir. I thank ICI Mangalore Center Chairman, Secretary, and Treasurer, and EC members for actively participating in the webinar actually. I thank Mr. Kaushik, Ms. Anjali, Officer Techno Marketing, QCrete Readymix India for coordinating the program. I thank all the participants for attending the webinar and constantly supporting QCrete webinar series in large numbers, keeping us motivated to conduct more and more webinars with the topic related to concrete actually. Thank you all. Thank you very much, sir. Thank you, sir.
Thank you very much, and see you soon.
Yeah, it was one of the best relevant topics which we had heard after a long time actually, because it's the most debated topic actually.
Yeah, this is an interesting and controversial topic, yes. But we will see you soon on the 2nd of December, I think.
Yes, sir.
Okay.
Yes, sir. Nice meeting you, nice hearing to you, and it was glued to the entire topic, glued to the complete PPT is what you are presenting actually. So thanks a lot, sir, for coming on to our webinar series actually. Thank you very much.
My pleasure.